So the next thing is that uh, when under what conditions this limiting right continuous non-decreasing function f is a distribution function, and that is answered in this theorem, which says that fn, uh, the distribution function f in the Haley selection theorem is a distribution function if and only if fn is tight. So if fn is tight, then the limiting subsequent limiting function f in Haley selection theorem is a distribution function. And same if the limit if the every subsequent limiting distribution f in Haley selection theorem is a distribution function, then the fn is tight. So let's prove that. Let's prove the first direction. If fn is tight, we want to prove that f is a distribution function. So we know fn is tight, so we for any given epsilon, there's m epsilon that this lim sub is less than or equal to epsilon. So from this fn, if we let fnk be a subsequence of fn, such that fnk converges to a non-decreasing right continuous function f, and then if we look at if we then for all minus x less than or equal to minus m epsilon and x greater than m epsilon, we have 1 minus fx plus f minus x, which is the limit of the corresponding fn case, right? And this is less than or equal to the lim sub of fnk m epsilon, because x is greater than m epsilon, and this 1 minus fnk x is less than 1 minus fnk m epsilon. Same for this term, minus x is less than minus m epsilon, then this fnk is less than or equal to this one. But we have by assumption we know that this is less than epsilon, so we know that this one is less than epsilon. And since this is true for all x, if we take the limit x, if we take x to be the limit, it goes to the infinity, then we get 1 minus f infinity plus f minus infinity equal to 0, which indicates that limit of fx when x goes to infinity is 1, and f minus x when x goes to infinity is 0, which concludes that f is a distribution function. Now we prove the other direction, which is that if every subsequent limit function f in the Haley selection theorem is a probability distribution function, then fn is tight. So let's suppose fn is not tight. In that case, we want to prove that we want to find a contradiction here. So if fn is null type, which means that there exists an epsilon and a subsequent nk such that 1 minus fnk on value k plus fnk on value minus k is always greater than epsilon, right? So for any number k, we can always find nk such that this is greater than epsilon. So the subsequence we selected here, and fnk, will satisfy this inequality for all k. By the Haley selection theorem, now we use the Haley selection theorem. Then this subsequence fnk, there's a further subsequence nkj such that this further subsequence fnkj converges to a function f for all continuous points of f, and But this f, which is a distribution function, and by assumption, that's by the assumption of this direction. So so uh, so 1 minus fx plus 1 f minus x, which is a limit of this further subsequence, but this further subsequence is greater than or equal to when j goes to infinity, it's greater than or equal to fn kj on kj plus fn kj minus minus kj. So this term is greater than or equal to this term. This term is greater than or equal to this term. But this is um, greater than or equal to epsilon. So and epsilon is greater than 0. So if you take the limit of x, and this is true for all x, so if we take the limit x to the limit, we have 1 minus f infinity plus f minus infinity is greater than epsilon, which contradicts that f is a distribution. Therefore, fn is tight. So that's proving the other direction of this theorem.